Mathematical principles are often taught as abstract, isolated concepts, but when that exact same geometry is applied to a physical material to build a load-bearing structure, it becomes complex engineering. A persistent critique of modern STEM education is its reliance on a decontextualized, Eurocentric approach. The curriculum frequently asks students to solve for variables in a vacuum, completely divorced from their physical reality. This abstraction contributes to a documented achievement gap. When students cannot connect formal mathematical logic to their lived environments or cultural backgrounds, engagement drops and comprehension stalls. To solve this, researchers and educators are testing a pedagogical framework known as Ethno-STEAM, integrating science, technology, engineering, arts, and mathematics directly with indigenous knowledge. The mechanism here is specific. It requires taking the formal, rigorous competencies required by standard STEM curricula and embedding them inside local cultural practices. Cultural heritage functions as a live dataset, a physical site for rigorous scientific and mathematical inquiry. Utilizing local context as the primary vehicle for mathematical reasoning offers a path toward reconnecting theory with a student's lived environment. We can see this applied directly through the vernacular architecture of Indonesia, specifically the traditional Minangkabau Gadang house. Structures like this are typically analyzed through the lens of art history or sociology, while the immense structural engineering required to make them stand upright is largely ignored. The building features intricate carved facades and elevated stilt structures that must constantly balance weight and negotiate the physical forces of their surrounding environment. This introduces the concept of ethnomathematics. This is the inherent mathematical logic, spatial reasoning, and geometric rules embedded within traditional cultural practices. The original builders did not use modern academic formulas, but they utilized complex geometry and load-balancing techniques unconsciously, passing this highly functional engineering down as cultural tradition. In 2024, researchers Haryanto, Samsudi, and Arborini designed an Ethno-STEAM educational intervention to systematically reverse engineer this specific architecture inside the classroom. The project uses the Gadang house as a complex engineering blueprint, presenting students with a structural puzzle they must solve through formal logic. The delivery mechanism for this intervention is project-based learning, or PGBL. This shifts the student from a passive absorber of data into an active engineer. The assignment was precise. Students had to design and physically construct accurate miniature models of the Gadang, Katidiang, and Kombuk houses. This type of assignment is an ill-structured problem. That is a real-world challenge lacking a simple formulaic answer, which forces the student to synthesize multiple disciplines to reach a solution. The project operated on a strict constraint matrix. First, the miniature models had to be structurally sound, requiring the students to perform formal STEM calculations to ensure stability. Second, the models had to strictly maintain the aesthetic, cultural, and proportional integrity of the original indigenous architecture. A standard textbook problem usually isolates a single variable and provides all the necessary inputs, but this constraint matrix does the opposite. Students cannot guess their way through the physical bill. They have to extract the required data themselves, translating the physical shape of the house into actionable mathematical equations. The cultural aesthetic acts as a strict parameter. To successfully complete the physical project, the students are forced to execute precise mathematical reasoning. To begin constructing the Gadang miniature, the students had to satisfy specific mathematical requirements. First, students analyze materials to design the rectangular floor plan from a top-down perspective. They apply geometric formulas to calculate surface area and material needs. Next, they move to the most complex architectural feature, the dramatically sweeping curved roof. Replicating this curve requires advanced spatial reasoning to bend flat materials into complex 3D geometry. This introduces structural loads. The sweeping peaks create uneven weight distribution that must be transferred safely to the support columns below. Without precise angle calculations and load-bearing mathematics, the tension of the curved materials will cause the miniature roof to collapse. Students continuously cross-reference the physical build with their mathematical proofs to ensure the structure remains stable at every stage of construction. In this process, the architecture itself acts as the teacher. If the mathematical calculations are incorrect, the physical model provides immediate, undeniable feedback by failing. To successfully build the cultural artifact, the student is essentially performing advanced structural engineering and calculus. The physical construction is only half the study. The other half is the empirical evaluation of the learning module's efficacy. The researchers established a baseline measurement by testing standard numeracy literacy levels in classrooms utilizing traditional decontextualized STEM curricula. This chart shows the primary objective outcome of the study. After completing the Gadang house project, students demonstrated a measurable, quantifiable improvement in their numeracy literacy compared to the baseline. Alongside the test scores, researchers documented a secondary outcome, a psychological shift in student engagement and motivation. The learning model connected formal schooling directly to the students' own lived environments and cultural identities, giving the abstract math immediate, recognizable stakes. That higher engagement directly correlated with increased persistence. When students hit friction trying to calculate the ill-structured problem of the roof design, they kept working until they solved it. This active, motivated state is the opposite of the passive alienation often recorded in standard, textbook-driven mathematics classrooms. The Ethno-STEAM framework operates as a verified, data-backed mechanism for raising objective academic performance. The Gadang house experiment demonstrates a specific change in how we integrate local knowledge with formal science. Indigenous knowledge and cultural artifacts possess an inherent, rigorous mathematical logic that is waiting to be utilized in the classroom. Grounding abstract engineering principles in tangible cultural projects effectively bridges the comprehension gap for diverse learners. Students apply theory as active mathematical innovators within their own heritage, using indigenous logic to solve contemporary STEM problems. For curriculum developers, the directive is clear. To teach 21st century STEM skills effectively, we have to systematically reverse engineer the engineering of the past. Ethno-STEAM proves that some of the most advanced mathematical tools we have for the future are already built directly into the architecture